Okay, hello, ap2, chapter 12, part 2. You might be wondering where was part 1? Well, that was the mechanical universe. We'll call that part 1. Here we are, part 2. Today, among other things, we're going to learn about the Carnot cycle, we're going to learn about efficiency, and we're going to learn a little bit about entropy, and we'll learn that the entropy of the universe always increases, and as such, that makes the concept of traveling back in time quite difficult. I know, right? Thermodynamics, time travel? Oh, you'll see, we'll get there. First, a quick little review. So far, we know the 0th law of thermodynamics. That is our law of thermodynamic equilibrium. If A and B are in thermodynamic equilibrium, and B and C are in thermodynamic equilibrium, the 0th law says that A and C will be in thermodynamic equilibrium. 0th law. Alright, the first law of thermodynamics. The first law of thermodynamics says we can't get a greater amount of energy out of a cyclic process than we put in. This is conservation of energy. You cannot get a greater amount of energy out of a cyclic process than you put in. You can't put 10 joules of energy into a machine and get 100 joules of work out. This is conservation of energy, and mathematically we expressed this like this. That the total internal energy comes from heat and work. I dump in heat, I dump in work, and all of it can be accounted from in any of those three places. So we're just conserving energy. We're moving it around from one point to another in various different ways, but it's being conserved. So this is the law that says the best you could ever hope to do is break even. And the next one we have is the second law of thermodynamics. The second law of thermodynamics says that no heat engine operating in a cyclic cycle can absorb energy from a reservoir and use it entirely for the performance of an equal amount of work. What that means is no engine ever can take in heat and use all of it to do work. Heat has to go in, some work can get done, but some heat has to leave. Now, in something like your car engine, the heat is actually being removed on purpose. You're using a radiator to purposely fully remove heat, and that is so that your engine doesn't thermally expand and destroy itself. But even if we didn't mechanically remove heat from an engine, no matter how effective we make it, there's always going to be friction, and with friction you're always going to have materials rubbing together, and energy will be lost due to that, if nothing else. So no matter how we play it, heat goes in, some work comes out, and more heat comes out. So you got heat going in hot, work gets done, heat comes out on the cold end of the cycle. Okay? This law says that although the first law states the best you can do is break even, the second law says you can't even break even. You'll never even break even. Okay? So, a review of the thermodynamic laws. The next thing we should talk about is the Carnot cycle. You saw this in pretty great detail in your in that mechanical universe video, but I just want to go run through it here at this point. So, we're going to need, for the Carnot cycle, a piston. And I'm going to want to draw this piston a few times, so I'm going to copy it now. There we go, copy, and I'm going to want to make a couple more of them, so I'm going to put another one, oops. How do you paste? There you go, paste. Move that one down here, I'm going to want another one, so I'm going to put another one here. Paste. Okay, so how many do we have now? Is that 3? Yep, I want one more of these. Let's draw one more here. Oops. Paste. Okay. Here we have our 4 pistons ready for the Carnot cycle. So the Carnot cycle, we'll say it starts off with isothermal expansion. So isothermal expansion. In other words, the piston's going to go that way. During this step, we actually bring a source of heat and we push heat into the system, and this happens at high temperature, so we'll call it hot, okay? Now, because this is isothermal, there will be no change in temperature, which means there will be no change in the internal energy, which means any work that's getting done, this being the work, is going to come at the expense of the heat you're putting in. So I'm putting in heat and I'm getting some work done isothermally. This is the first part of the Carnot cycle. The second part of the Carnot cycle is going to be adiabatic expansion. So the piston's still going that way, except this time there's no source of heat being added. The amount of heat being supplied is 0. We're not adding or removing any heat, which means the change in internal energy is going to come entirely at the expense of work. Another way to say that, the work that's being done, this being the work, comes entirely at the expense of the internal energy of the gas. Now, because I've done that, because the work got done, the internal energy had to have paid for that, that means during this phase, the gas is cooled down. During this, internal energy was spent to do work. So the temperature of the gas went down. And this is the most brilliant part of this. Because the temperature went down, that means during the next part, which is our isothermal compression, we want to recompress the piston because we want this to be cyclic, so I've pushed the piston out. Now I need to pull it all the way back in so I can push it back out again. We want this to be a cyclic process. Now that I'm going to compress, the way I'm going to do this is I'm going to let heat come out, and we'll call this on the cold side. And because the temperature dropped in the previous step, the temperature here is now a colder temperature, a cooler temperature. But this is where it's so amazing. A cold gas is easier to compress than a hot gas. A cold gas means that all the particles have less kinetic energy, which means it takes less effort to actually squeeze them together. So we dumped in energy, the gas expanded, the gas continued to expand, doing more work while cooling down. Now we're going to be compressing a gas that's cooler. So now we expanded a hot gas, but we're compressing a cool gas. That takes less energy. The difference in those two energies is the amount of work we got done. That's pretty cool, actually, in case you were wondering. At any rate, this is an isothermal process, so during this phase there is no change in temperature, and that means there will be no change in internal energy, meaning that any work getting done, the work getting done now is going to be in that direction, is going to come entirely at the expense of the heat. Isothermal compression. Okay, and then the last step is we let this continue to compress. No heat's being removed. We're going to compress this adiabatically. Adiabatic compression. Okay, now because there's no heat being exchanged, that means that the work being done, this being the work, and remember it's negative work from the point of view that we're talking about, pushing it up is the positive work. But at any rate, the work being done has to come from the expense of the internal energy. Now, the work being done here is the opposite than before. So last time we had an adiabatic phase, the temperature went down because we were losing internal energy. This time we're compressing, which means the internal energy is going to increase, which means in this phase we actually have a temperature increase. And that temperature increase sets us up to be hot again, and because we're hot we can add heat to the hot gas and we have our isothermal expansion and the process continues. This is the Carnot cycle. The Carnot cycle is a theoretical engine. It cannot exist in reality, but the reality is this is the best you could possibly get. This is the most efficient engine that you can build. And it's not 100% efficient, but this is as best as you can get. And this is Carnot. So the next thing to talk about, and you saw a lot of this in the video there, but the next thing to talk about, oh yeah, by the way, on tests you often hear Carnot cycle, but you'll also hear phrases like the most efficient engine, or nature's best engine, or nature's most efficient. Whenever you hear phrases like that, they're referring to Carnot, they're referring to this. All right, I want to step away from the Carnot cycle for just a moment and talk about efficiency. I mentioned the Carnot engine is the most efficient engine. Well, let's look at efficiency in general, and then we'll look at efficiency of the Carnot. So in general, I cannot spell. In general, efficiency is just going to be your benefit over your cost. What do you get out of it, and what do you have to spend to get it? Benefit over cost. Well, in terms of a thermodynamic engine, the benefit is going to be some amount of work, and the cost is going to be some amount of heat. And I'm going to call it heat on the hot side because, if you remember, that's just where we happen to randomly talk about the beginning of our expression. So we're going to do it that way. So we've got efficiency is benefit over cost. That's work over heat. Now, if you remember, the work we're getting done is the difference between the heat we put in on the hot side and the heat that leaves on the cold side. Remember, no matter what we do, we have to put heat in. Work can get done, but heat has to come out. So some heat has to go in and some heat has to go out. The difference between those two will be the work you get done. And that work is divided by the cost, which is the heat you put in. Well, that reduces to 1 minus the heat on the cold side over the heat on the hot side. And in general, that is an expression that'll give you the efficiency of a machine. And because the heat on the cold side is smaller than the heat on the hot side, this is less than 1, the efficiency is less than 1, less than 100%. Okay, so there's the efficiency in general. Now, for a Carnot engine, it turns out energy is still not conserved, so we have to put heat in, get work done, and some heat has to come out. But although energy is not conserved in a Carnot engine, something is. And that something is called entropy. Entropy is conserved in a Carnot engine. Now, in general, entropy is not conserved. In general, the entropy of the entire universe always increases. I'll show you in a few minutes how this works, but you can design an experiment that will actually result in a decrease in entropy. But if you do an experiment that decreases entropy in that experiment, somewhere else in the universe, necessarily there will be an even bigger increase, providing you a net increase in entropy. Carnot is theoretical, Carnot is idealistic. In a Carnot engine, entropy is actually conserved. And this is why it's a theoretical engine. Entropy can't be. But in a theoretical Carnot engine, entropy is conserved. Entropy is simply the heat that goes in divided by the temperature at which it goes in. So the ratio of heat to temperature gives you something called entropy. Now, if we imagine the entropy at the hot side, we'd write it like that. Now, for a Carnot engine, there's no change in entropy. So the entropy at the hot side has to equal the entropy on the cold side, right? And that means that, what am I doing? That means that that is true for the Carnot. Now, if that's true, that means that if I rework this, cross multiply, that the temperature on the cold side over the temperature on the hot side is equal to the heat on the cold side divided by the heat on the hot side. And if we go back a second and look at our equation for entropy, that is that. So for a Carnot engine, we can write that the efficiency is 1 minus the ratio of the temperatures. And we can get away with that because for a Carnot engine, the ratio of the temperatures actually equals the ratio of the heat because you're not actually changing entropy. Entropy is conserved there. All right, let's go talk a little bit more about entropy. Why does the entropy of the entire universe always go up? Well, let's imagine a thermodynamic process in which we're just going to have a simple thermodynamic process in which we have some state A, and we're just going to say that A is going to be at some hot thing. So let's just say A is going to be at some temperature TA, and let's say we have some chunk of something B, and it is at a temperature TB, and let's just say that the temperature of A is greater than the temperature of B. So A is going to be the hot thing, and B is going to be the cold thing. So if A is the hot thing, then that means we'll take some heat, QA, and we'll take some heat, QB. Now let me not say it that way. Hold on. I thought of a better way to think this. When I put these two things in contact, energy is going to go that way, right? Energy is going to leave A and go towards B, right? So let's just say, for putting numbers on its sake, let's just say that the temperature of A is at a temperature of 10 units. Let's say the temperature of B is 5 units. So A's hotter, B's colder. Okay, let's just say that we put these in thermal contact, and once they're in thermal contact, energy is going to transfer, and energy is going to be Q. So let's just say that we watch the process until 1 unit of energy is transferred. Okay, 1 unit is transferred. So once 1 unit of energy is transferred, the entropy at A excuse me, is going to be the heat that left A, well, 1 unit left A, at the temperature of A, which is that. And let's look at the change in entropy for B. Well, 1 unit of heat entered, so notice A is negative, B is positive, but B is at a temperature of 5. Well, net, excuse me. Excuse me. Which means that even though during A I managed to have a decrease in entropy of 1/10, that experiment resulted in B showing a increase in entropy of 1/5. That means overall there has been a net gain in entropy, right? If I add the entropy of A and the entropy of B, I end up with a positive value. The entropy of the universe absolutely increased, and it is unavoidable. Entropy always increases. Well, if entropy always increases, that makes going backwards kind of difficult, because if I go backwards in time, you would expect to go back in time to a time when the entropy was smaller. The entropy a couple years ago was smaller in the universe than the entropy is now. But if I go back in time, that is going to be that will in some way or another result in some sort of thermodynamic process, and as a result, the entropy of the universe will go up. So if the entropy is going up, I cannot go back to a place that has lower entropy. That will cause the entropy, it can't work. So let's see, I think that is everything I feel like we should say about this chapter. I'm going to go ahead and call it here. We'll work some problems in class.